Good morning, neighbors. Hope the coffee's warm. Pardon. So, I put a link to a video in the description, or I will have, hopefully by the time you see this, that explains how a capillary column works. Now, what the heck is a capillary column? That's a good question. Basically, you take a tube and you put a coating on the inside that has some really neat properties. And when you run a gas through it, it can separate the different molecules in the gas because they're shaped different. Now, there's much more to this story than the video shows, but the video shows enough to be an interesting story. This is how that little pipe flow is just a part of the physics of gas flow, where two surfaces meet. A gas surface and a solid, in this case, inside a pipe. And tiny little interactions that happen at the boundary of the surface of that pipe. Now, in the case of a capillary column, those are microcolumns. They're very, very tiny. And the length of them is an engineered length so that those separations can happen. And when you set the column up, the gas flow rate through the column is a part of what you need to know because you're timing how quickly those little pulses come out of the end. And those little pulses, you're assuming they're hydrogen, they're nitrogen, whatever the constituents are, methanes, CH4s. Each different shaped molecule is going to bounce off that wall a little bit different. So as it travels up, and you do add gravity onto these columns, it is an effective part of the action of the column to evenly coat the column instead of having the bottom of the pipe kind of build up a little more than elsewhere. So that little 2-minute video really is, it's one of those doors. It is a rabbit hole trying to understand how those little particles can separate out like that. And take my word for it, there's more to it than that little video shows. How you inject that gas sample into your measurement capillary column is a way cool mechanical thing at this point. So, yeah, that's a pretty neat little video. And again, it's a, question on a quiz somewhere you didn't realize, something you didn't care about, you didn't need to know. But those are the actions of molecules interacting with other molecules. Atomic, it's not subatomic, this is atomic. This is, atoms, elements, isotopes that are in a structure combined with other things. That soup has 100 and some odd elements in it from the periodic table, or could have, any of them. So that's a really simple gas example. And again, I think I've watched it 3 or 4 times already, and I took the course long ago. And yet it's a good presentation of it, and it's in color. So that's good. Now, you look at those properties. Again, 2.5-minute video, where can you go with that? You look at those properties that they're explaining, they use repetitively and over in a gas analyzer to get results of a question of what something's made up of, its content, its properties, curiosities. Man, dead cats to the walls. So look at that video, cool as it is. I mean, it could be better, right? But now, let's go to the pipes underground in Flint, Michigan, where the pH of the water released chemicals, elements that had been stuck against the walls of those pipes for decades. These are things we knew about. By we, I mean me and the mouse in my pocket. So there's that little picture, that little really doesn't mean anything 3 or 4 minute video like most of mine, that opens up how you understand possibilities in fluid dynamics. So print yourself a degree, but this little piece you can be confident that chemistry, that physics, that turbulent flow is how things work. And some people understand that. And it doesn't matter when you turn your tap water on. It shouldn't matter. You should just have drinkable tap water. You would assume that was kind of the point of putting the tap in your house in the first place. So, I hope this comes out as good as I hope it come out. Pieces out. It's fun putting them together.